Hi everyone, I'm Antonino Agostino from Baker Hughes and I will present our work titled Controllable Image Synthesis of Industrial Data using Stable Diffusion. Automatic defect detection is a crucial problem for industrial applications, as it allows to ensure high-quality industrial products. Supervised deep learning offers methods for defect detection having high performance levels. Sometimes they are even superior to human levels. However, optimizing supervised defect detectors needs large-scale, fully annotated datasets, which are hard to obtain in industrial environments because engineers strive to optimize real-world industrial procedures and minimize the number of defective products as much as possible. Lastly, producing high-quality annotations is costly and often requires experts. In the literature, there are several approaches that try to address the lack of annotated data. Zero-shot and few-shot learning still do not address the problem of data scarcity in real-world scenarios, because they train models using only small amounts of annotated samples, while leaving them ignorant about the entire data distribution, which can be complex and have many unseen modes. Multitask learning offers exciting perspectives, but it is hard to optimize because it requires difficult optimization processes and careful loss balances. Instead, generative models offer opportunities for synthesizing realistic data conditioned on input classes, text, or geometrical constraints. Unfortunately, training good conditional generative models from scratch may also require large-scale annotated datasets, leaving their applicability in industrial environments confined to limited settings. So, how can we reduce data requirements? To address the lack of data, we introduce a novel data generation approach that exploits a general-purpose image prior previously acquired on large-scale datasets. In particular, we tune Stable Diffusion to first learn application-specific concepts and then to generate images conditioned on specific requirements. By doing so, we make it able to generate self-annotated synthetic data that can be used for downstream tasks. In general, natural images used to train foundation models are not representative of data distribution encountered in industrial environments. The picture you can see here compares the idea that Stable Diffusion has about the concept the inside of a gas combustor with the real images. It's evident that directly using pre-trained image priors for generating industrial data is not feasible. So, we adapt the foundation model to learn the new concept represented by the data of interest. We do that with DreamBoot, which allows Stable Diffusion to learn new concepts while preserving prior knowledge about generic image appearance and avoiding catastrophic forgetting. After learning the new concept, we tune a hypernetwork using an input topological driver to condition the image generation. First, we extract the topological driver from a small subset of labeled defective images, using the pipeline shown in the picture. Then, we make the model able to produce an image matching the topological driver and showing a defect corresponding to the defect mask inside the driver. The resulting model is then able to learn the mapping from the topological driver space to the image space. As depicted in the figure, our method successfully synthesizes realistic images. Notably, the global topology of the generated images follows the geometries in the input driver. They also show defects whose appearance is coherent with the given defect masks. We investigate if we can use the self-annotated synthetic data on a real industrial use case, consisting of training a model to perform instant segmentation of cracks. As can be seen in the chart 1, synthetic data allows to increase model performances according to all the considered metrics. We also provide results obtained by training our method only on synthetic data, showing that synthetic images well represent the data distribution and allow to train a good detector with no real data at all. Results shown in the chart 2 demonstrate that training high-capacity instance segmentation models such as mask RCNN with such a small dataset is not feasible, and the model collapses. Experiments also show that our method increases variety with respect to in-painting methods. You can refer to the paper for ablation studies and additional experiments. To wrap up, we explored image generation for real industrial problems. We introduced a novel approach for conditional image generation of industrial data based on two phases. We generated high-quality self-annotated data using only coarse topological drivers and arbitrary defect masks. We validated synthetic data utility in challenging downstream tasks. Measuring large performances increase with respect to using only real data. Results highlight the high potential of generative AI for vision applications in industrial problems. Thanks for the attention.